Right, so in the last class, we were analyzing projectile motion, which is this classic two-dimensional problem with constant acceleration. You have some object that is 0369 is the attendance code, I believe. 0369. So you launch a projectile with some initial velocity v naught at an angle theta naught. And this is two-dimensional motion with constant acceleration because once it's launched, the only acceleration it experiences is due to gravity, which is pointing straight down with a magnitude of 9.8 meters per second squared. And there is no acceleration along the x direction. And so we take our general equations of motion along the x direction and our general equations of motion along the y direction. And we identify that ax is 0, that ay is minus g in a coordinate system where the positive direction is chosen to be upwards. And then we do a little bit of trigonometry here. Given the initial speed and launch angle, I can break up this velocity vector into its x and y components, where v naught x is v naught cosine theta naught, v naught y is v naught sine theta naught. And I put my origin in this particular problem. I made a choice, put the origin right there at the launch point so that my x naught and y naught are both 0. Any questions on that? So once I plug in this information into these general equations for the x and the y directions, they can be reduced to this, I guess, slightly nicer looking set of equations. Once again, these are all the equations for the x motion, and then these over here are the equations for the y motion. And then we are basically going through a series of questions and trying to answer them, and it kind of gives you some practice in how to kind of manipulate these equations and how to think about them. And then on WebAssign, you'll have some more example problems. So one question may be, what is the shape of the trajectory? That is, find y as a function of x. So here, you can think of this curve as essentially a plot of y as a function of x. For every value of x, there's a particular unique value of y. And so what is that y as a function of x? Maybe a WebAssign problem is something like, once it's launched at this speed and this angle, what is its height when x is a half a meter or something like that? Then one way you might do that is to simply determine what is y as a function of x. Once you have that, you can plug in x equals a half meter and then see what the y is at that point. Any questions on that? And so I see here that there's an equation where y is a function of time, t, but I want to get y as a function of x, so I want to eliminate the time variable. And while we can analyze the x and the y motions separately, at the end of the day, they are linked to each other ultimately through the time variable, right? Because at a given time, the object will have a particular x and a particular y. It's not random. At a given time, there will be a particular x, and for that particular x, there will be a particular y. So the time variable, in some sense, ties together the equations on the left and the right. So you can see here the x component of the velocity is just a constant. So there's no real sort of time dependence there. The only thing that depends on time is the x coordinate. So there's a time variable here that talks to the time variable appearing in the equations on the right. So here I have y as a function of time, and here I have x as a function of time. So I look at those two equations. I use this first equation here to solve for time as a function of x, eliminate the time variable in favor of the x coordinate. And once I have this, I can use this equation for the time in my equation for y as a function of t. So wherever I see t, I can now replace it by this equation 3. And so once I do that, I get this here. You do a bit of algebra, you end up with y as a function of x. And we see that it has a quadratic dependence on x. So that's a parabolic dependence. And then because it's with the minus sign multiplying the x squared, it looks like an inverted parabola. And so now if someone says, yeah, go ahead.
Tangent instead of sine?
I'm doing sine theta divided by cosine theta, and that's tangent. So I just combine those two into tangent. Yep. Any other questions? The next question we looked at was, what is the maximum height reached by the projectile? So in terms of pictures, it's saying, what is this height right here when it is at its maximum value of y from above the ground? And again, we use these 6 equations here and see what we need to find. To find the maximum height, is there a question?
Oh, no, sir.
Oh, okay. To find the maximum height, essentially we want to find the y coordinate whenever it's at its highest point. But it's not quite obvious how you would use this to find the maximum height, because this is a y equation for all values of y. So how do we isolate what is special about the maximum height? Well, at maximum height, we know that the y component of the velocity is 0. So we immediately identify that. We know that at maximum height, the y component of the velocity is 0. And so what I can do is, in fact, if I set y equaling, Vy equaling to 0 in this third equation here, then I could just go ahead and solve for the y when Vy is 0, and that's going to give me the maximum height. Any questions on that? And so I do that when Vy is 0, I get this, solve for y, and then I get this answer. And so again, you can basically measure this maximum height if you know the initial speed and the launch angle, and then you can determine what is the launch speed. So if you're trying to determine the speed with which some device launches a projectile, this is a simple way to experimentally determine that. And then finally, in the last class, we looked at what is the range of this projectile, which is essentially this distance here. That is, you launch it from the ground and then you see how far it travels before it falls back on the ground. That's this distance here, the range. And so once again, we look at our 6 master equations here, and we try to figure out what is special about this particular point here, the range, when it's back on the ground. Well, we know at that point, the y is 0 again, or the y is equal to y naught. This initial y is equal to the final y is 0. And then I want to find what is this range, which means I want to find what is the x coordinate when it hits the ground. And the only equation here that's telling me something about the x coordinate is this second equation here. So I want to know what is this x at the moment that the projectile hits the ground here. But in order for me to know that, I need to know what is the time when the projectile hits the ground over here. So if I can figure out at what time it arrives here, I can plug that in here, and then that's going to give me the range. Any questions on that? So just to recap of what we did last time. So in order to solve for the time variable, what I can do is use my information that y is equal to 0 over here. So if I set y equaling to 0 here, then I have an equation that I can use to solve for the time variable, and that's this equation here. And then once I solve for the time variable from this equation, I can plug it in here to get the range. And so I'm going to use these 2 equations to figure out the problem. And then what I do here is in this equation, I can factor out a t from both sides, from both terms. And then you get 0 is equal to t times this thing here. And then turns out, because it's a quadratic equation in t, there are 2 solutions. One is that either this t is 0 or this thing in brackets here is 0. Those are 2 possible ways in which this left side could be 0, right? So the t equaling 0 Well, that's just sort of the trivial solution because that's just telling you that this condition y is equal to 0 is true at two places. Y is equal to 0 here at the initial point. That's when t is 0. And then y is also equal to 0 at this final point. And so we're seeing the two solutions. So this t equaling 0 is just corresponding to the initial launch point. So obviously the t that we need when it hits the ground is by setting this guy here to 0 and then solving for t. Whoops. Right, so this guy here. So either this guy here is 0 or this bracket here is 0. Those are your two options. And so therefore we get, this is of course the solution that we want. And then once we have this solution, once we have this time, I can now substitute that in here, plug that in here. So that's my V naught cosine theta naught times t, which is all of this, which is that. And that here is equal to my formula for the range. Any questions on that? And so again, one of the things I want to kind of emphasize is don't walk around with, this is like a range formula, and then there's this formula, etc. Again, at the end of the day, all you need to do to solve any of these problems is just know these equations right here. That's it. There's really just three equations, one copy for the x, one copy for the y. From that, you can get everything. That is really all you need on your note card. If you try to start memorizing all the formulas for every situation, then things tend to get kind of out of hand. Let's see, there's a question in the chat. Wouldn't you multiply it by -2 to find it? I'm sorry, I missed. Can you, where should I be multiplying my -2? The person who wrote the question. In the final equation. In this final equation for the range. Now, I don't see why I would multiply by -2. I'm solving for the time here. So that's this, and then I'm plugging in the time here. And then I end up with this equation here. Does that answer your question, or? Let me know if it's still unclear. Okay. So let's look at, and by the way, so this is that range formula that we just derived. That is the range. You give me the initial launch speed and the velocity. It turns out that there's a trigonometric identity that the sine of 2 theta naught is the same as 2 times sine theta naught cosine theta naught. This is sort of a fact of life. It's a trigonometric identity. So often people will take this and take the 2 sine theta cosine theta and write it as sine of 2 theta. So this is often a more convenient way of writing the range formula. Questions on that? So let's look at this range formula for a bit and see if it makes sense. First, notice that in this formula, the range will increase if we increase the launch speed V naught. So that makes sense. The greater speed with which you launch something, the further it's going to go. But here's the tricky and non-trivial part, which is that you notice that if theta naught is very small, then you get something like sine of 0 almost. then the range is very small, right? Because the sine of a small angle is a small number. And so therefore, when theta naught is very small, the range is very small. Does that make sense? It does, because if theta naught is very small, then basically you're shooting the projectile almost horizontal to the ground, right? So you're not giving it enough height, and so it's just going to run into the ground very quickly. And so therefore, if theta naught is 0, your range is 0. You're just going to hit the ground. If you launch it parallel to the ground, it's not going to go anywhere. Does that make sense? On the other hand, notice that if theta naught is too big, let's take the extreme example where theta naught is 90 degrees. If theta naught is 90, that means you're launching it straight up. Right? When theta naught is 90, then you're launching it straight up. What should the range be? Anyone? If I launch it straight up, it's just going to go up. It's going to fall back down. So it's not going to go at all in the x direction. It's going to have 0 range. And you see that that works out, because if theta naught here is 90, then sine of 2 times 90 is sine of 180 degrees, and the sine of 180 is 0. The sine of pi is 0. So what that means is if you launch it at too low to the ground, the range is small. If you launch it too straight up, the range is too small. So therefore, what is the optimal angle with which you want to launch this? Well, if I look at this formula here, the optimal angle for launch is when this sine of 2 theta is 1, because sine is a function of an angle whose maximum value is 1. So whenever I can maximize this sine of 2 theta to 1, that angle is going to give me the biggest range. Any other angle will give me a smaller range. And we know that sine of 90 degrees is 1, which means that 2 times theta naught should be 90 degrees, which means theta naught should be 45 degrees. So if you launch it at exactly 45 degrees, you will get the maximum range. Any questions on that? So here's that in pictures. So notice that if you were to launch something at very small angles, they have a small range. If you launch them at too high of an angle, also they have a small range. But if you launch them at 45 degrees, then they have the maximum range. Right, so this is for a launch speed V naught of 50 meters per second. These are the different ranges that you get. Any questions on that? Okay. So hopefully that kind of gives you some sense of how to manipulate these types of problems. Let's come back to a question that I had asked you guys a couple of classes back, or maybe it was the last class. I'll ask you guys this question again to see if you guys have, did anyone have heated arguments about this problem? No? Okay. There's too much going on. So once again, here the question is that there is a target here. Someone is aiming their gun at the target along this line of sight. And as soon as this projectile is launched, the target at the exact same moment is released and starts to fall. And then the question is, will this projectile eventually hit the target, or will it miss? That is, because this target is falling when it is as soon as this projectile is launched, do we have to somehow compensate and probably aim this projectile a bit lower so that it catches this falling target? Or should we aim it directly at the target and then it's going to hit? Or should we aim it at some other angle? And so again, the question is, if I were to aim it directly at the target, launch it, will the target be hit or will it be missed? So let me just do a quick top hat again. So what you guys think? All right, 7 seconds. Let's see what we got. All right, more people than last time say the target will be hit. And very few of you say that it will not be hit. I want to keep you in suspense. And let's see if we can actually figure this out. So let's actually work this out and see what's going to happen and see if we can actually set up the problem in a way that we can actually answer this question. So let's stare at this situation here and collect some initial information. So here we are told that there is some projectile that is launched from here. It is aimed at this target that's sitting over here. Let's say that the target is sitting at some height h, a distance d from where the projectile is launched. Right, so just give it some names, h and d. And let's say that the initial launch speed, let's call that v naught, and the initial angle is theta naught. And so let's collect some initial information for the projectile and for the target. So at the end of the day, what is the question that we're trying to figure out is the target is going to fall, the projectile is going to be launched. Are they going to hit each other or not? So how do we go about trying to even set up this problem from the point of view of, trying to sort of quantify exactly the question that we're asking? The question we're asking is that when the projectile crosses this particular location, that is when the projectile is at x equaling to d, we want to know what is the height of this projectile at x equaling to d. And at that same moment, we want to know what is the height of the target. Right. So somehow we want to know that at what time does this projectile cross at x equaling to d? At some time, it's going to cross x equaling to d. At that time, what is the height of the projectile? And at that same time, what is the height of the target? If the two heights are the same above the ground, then they will hit. If they're not, then they will not hit. Right, I've taken this word problem and I've sort of boiled it down to the math question that I need to figure out. Is I need to figure out what is the time at which this projectile crosses x equaling to d. And then at that time, what is the height of the target and what is the height of the projectile? If they are the same, then they will hit. Any questions on that? So in order to do that, let's go ahead and collect some initial information. For the projectile, it is launched from the origin. So its x naught is 0, its y naught is 0. Once it is launched, it's again in free fall. The only acceleration is due to gravity. So again, its ax will be 0. Let's choose our positive x and positive y as usual. Then its ay will be minus g, or minus 9.8 meters per second squared. What is its v naught x and v naught y? Again, those are just these components here, v naught x, and then here is your v naught y. And as usual, they are, this side here is v naught cosine theta naught, and v naught y is v naught sine theta naught. So this is the initial information that we have collected for the projectile. What about for the target? Well, its initial x coordinate is actually d, because it's way out here. So its initial x naught is actually d. Its y naught, which is this height over here, is h. So notice in this case, it's not 0 because it's at some location out here. So x naught is d, y naught is h. And then once it's released, again, it's in free fall. So again, its ax is 0, and its ay will be minus g, acceleration due to gravity. And its initial velocity, well, it's released from rest. So its initial velocity is just 0. It has no x or y component of velocity. Once it's released from here, it's just starting from rest. So its initial velocity is 0. Any questions on that? The first thing we can do is this initial launch angle theta naught is related to the geometry of this problem. So if this target is at a height of h, a distance d away, then obviously the tangent of this theta naught is h over d. So we can immediately write what is this initial launch angle? That is, with what angle should you aim the projectile? It should be with theta naught being the tangent inverse of h over d. This is the mathematical way of saying that you should aim your projectile at the target. Any questions on that? Okay. All right, so next, as I said, the thing that we want to find is at what time does this projectile cross at x equaling to d? Because once we can get that time, then we can figure out the heights of both the target and the projectile at that time and see if they're the same or not. So the next question here is, find the time it takes for the projectile to reach x equaling to d. So what I'll do once again is I will take this initial information and rewrite my x and y equations of motion for the projectile. So remember here, right, that you always have v equals v naught plus at, y equals, or I should say, yeah, bx, ax, like that, and then you have x equals x naught plus v naught xt plus 1/2 axt squared. And then you have vx squared equals v naught x squared plus 2ax times x minus x naught. And then you have an identical copy of that in the y direction, right? So those are your master equations. So if I look over here for the projectile, and the question here is, at what time does the projectile reach x equaling to d? Then I see that my ax is 0. So therefore, my vx is just equal to v naught x, which is just v naught cosine theta naught. X is equal to x naught, which is 0. So then I have V naught x times t, which is V naught cosine theta naught times t. Ax here is 0, so that doesn't contribute. And then you have Vx squared equals V naught x squared, and this term here is 0, and that gives you this. And then I look at my y equations over here. Since I'm OCD, let me just go ahead and write it. Vy will be V naught y plus ayt. Y is equal to y naught plus V naught yt plus 1/2 ayt squared. Vy squared is V naught y squared plus 2ay y minus y naught. So if I look at this equation here, Vy is V naught y, which is V naught sine theta naught, plus ayt, which is minus gt. And similarly, this is my equation for y. It's V naught sine theta naught t minus 1/2 gt squared. And then this equation here becomes V naught squared sine squared theta naught minus 2gy, because y naught here is 0. Any questions on that? So all I've done is taken my general equations, used this information for the projectile, and just collected them over here. And now the question I want to ask is, what is the time it takes for the projectile to reach x equaling to d? So I look through these equations here, and I know that x is equal to d here, so that is the piece of information that is given to me. Where can I use that piece of information? Well, x appears here. When this x is equal to d, I have an equation to solve for the time. Because along the x motion, it's moving with constant speed. X is speed times time. So therefore, I go ahead and use x is equal to d is equal to V naught cosine theta naught times t. And so therefore, t is d over V naught cosine theta naught. That is how long it takes for the projectile to cross at x equaling to d. And so now that we have this time, our next problem is to figure out what is the y coordinate of the projectile at this time, and what is the y coordinate of the projectile at the same time, and if they are the same, then they will hit. Any questions on that? So let's do that. For the projectile, let's try and find its height. Well, I can just go ahead and find what its y value is at this particular time. So since this is my y equation here, I'm just going to go ahead and use this time in here. And then you get V naught sine theta naught, d over V naught cosine theta naught minus 1/2 g, and then d over V naught cosine theta naught, the whole thing squared. So that is the height of the projectile at the moment that it crosses the x coordinate of the target. And now you can do a bit of algebra. You know that sine theta naught over cosine theta naught is just tangent of theta naught. You see that the V naughts here cancel. These two V naughts cancel. And so therefore you're just left with tangent of theta naught times d. Sine over cosine is tangent. And what else over here? You have minus 1/2 g, so that's g over 2, d squared, and then this thing squared is V naught squared cosine theta naught squared. So that is your height. And what we can now do is we can express this height in terms of the geometry here, in terms of this h and d and stuff, by basically saying, so this equation here is cleanly written over here. Notice that tangent of theta naught is h over d. So therefore, d times tangent of theta naught, well, that's just the height of the initial target from which it was dropped. Right, just using this relationship here, tangent of theta naught times d is just h. Any questions on that? And then here I have cosine squared of theta naught. Well, what is cosine of theta naught? in this picture, it's the adjacent side over the hypotenuse. So cosine of theta naught is d over the hypotenuse, which is the square root of h squared plus d squared. And so therefore this cosine squared is the square of this. And so you get a d squared and then h squared plus d squared in the numerator multiplied by this prefactor over here. So all I've done is taken my launch angle theta naught and just rewritten it in terms of h and d, which are the things that you would measure in your experiment, in your experimental setup. So once I plug that in here, simplify it, the d squareds here cancel, you end up with this. That is the height. So you see that it's obviously not going to go directly to the height h, but it's going to be a little bit lower than the height h by that amount. Questions on that? So now our question that remains is, this is the y coordinate of the projectile at the moment in time when it crosses at x equaling to d. Now our question is, at the same time, what is the height of the target that is dropped? So once again, for the target, there's only equations of motion along the y direction. So I use all of this information here in the y direction, and I will end up with basically these equations here. Vy is equal to v naught y, which is 0 because it's dropped from rest, plus the at, which is minus gt, a is minus g. Then the y is equal to the y naught, which is h, right? Y naught is h. I should say this y naught here. This y naught is h. V naught y is 0, so this term doesn't contribute. And ay is minus g, so you end up with minus 1/2 gt squared. And then there's this last equation, which is vy squared, which is minus v naught y is again 0 here. V naught y squared is 0, minus 2g times y minus y naught, which is that. And the thing we're interested is in the height. This is the equation that we're interested in. And we want to evaluate it at this particular time. So I'm going to go ahead and use this equation here and evaluate it where my time is this same time when the projectile crosses the x equaling d, d over v naught cosine theta naught. And therefore you end up with h minus gd squared over 2 v naught squared cosine theta naught squared. Holy crap, that is exactly the same as this right here. So in fact, the two will hit. Any questions on that? Okay, that was a lot of math to figure that out. It's a pretty non-intuitive thing. But how can we sort of intuitively understand that the projectile should hit? Well, let me ask the following. Imagine if we turn off gravity. We're in outer space and we set g equaling to 0, there is no gravity. And you're launching a projectile, you want to hit the target. How are you going to aim it? Anyone? No gravity. Say it again? I'm hearing a bunch of mumbling, but you aim it at the target, because in outer space, what's going to happen? You launch the projectile, you release the target's just going to sit there. There's no gravity, it's not going to fall. And what's going to happen to the projectile? There's no gravity, so you launch it, it's going to continue moving with a straight line. The acceleration ax will be 0, the acceleration ay will be 0. So if you launch it with v naught at an angle theta naught, it will continue with v naught at that same angle theta naught and it will then just go and hit the target. And now you turn on gravity a little bit. What's going to happen? The target is going to fall, but so is the projectile. And they kind of fall together. They were destined to meet when gravity was off. And now as you turn it, they both tend to fall kind of together. That's one intuitive way of understanding what is happening. Any questions on that? Let me see. I think I have a YouTube video on this. This one looks kind of fun. Okay, I have not seen this one before. So let me go to the safe one, the MIT physics demo.
Want the latest Amazon device? Get it now, pay over time with Amazon monthly payments. Break your purchase into
Okay. In case you're wondering what that was about, I guess this problem was written in the early 1900s or something. And they were talking about a hunter and a monkey dropping from a tree. And that's why that happened. Any questions on that? What happened here? Okay. Here's another sort of a simple example problem that I won't go over, but I'll kind of leave it for you to see. So again, there's a fighter plane here. It launches some projectile. It asks you a bunch of questions about it. So I'll just kind of leave that for you as some fun reading. All right, that brings us to the end of chapter 3 on projectile motion. Oh, I guess we're out of time. So yeah, let me go ahead and stop here, and I will see you on Wednesday.